precise references for this book. I got yesterday the information concerning the PDF file. So I give you the address where you can get it. So the book is called, as I said at the beginning, Uniformisation des surfaces de Riemann. Retour sur un théorème centenaire. I didn't give you the author yet. So it happened that, as I told you, the book was written as a collective work of many people. So we didn't think it could be a good idea to put many names on the cover. So we had a discussion what should be a good author. So we decided that the author would have a first name. The first name is Henri Paul. Henri is from Henri Poincaré, of course. And Paul is from Paul Koebe. And for the name, we decided that we chose the name of the village where we work together. So the name is de Saint-Gervais. So this is the name of the author of this book. Now, if you want to buy it, you can get it on the www. Le comptoir. This is the editor, and then you go to you search for uniformization, and you can click and you can buy it. It's not very expensive. And if you want the file, the PDF file, you can get it from here, or you can get it. I just put it on my web page, so you can download it. www. This is not IMPA, this is UMPA. PDF. And you have the file. Okay, so we are in the middle of trying to get a proof of the version of the uniformization given by Klein and Poincaré. We want to prove that any algebraic curve X of genus at least 2 is the quotient of the Poincaré disk by some discrete co-compact subgroup of PSL2R. Now I realized that, so I gave you the sketch of the proof. The sketch of the proof was to construct a map from from the space of discrete of homomorphisms from gamma fundamental group of X to PSL2R. So you have to take inside that space the subsets of those which are discrete and faithful, injective, you have to take the quotient of this by the conjugacy by PSL to R. So this is basically the set of Fuchsian subgroups of a given genus acting on the disk up to conjugacy, and you map that to what I call last time Riemann of G, which is the space of holomorphic structures on the surface of genus G up to isomorphisms homotopic to the identity. So we describe the map from this set to this set. We show that this map is injective. And the idea is to show that it is bijective. Now, I just realized that if I want to give all details, it would take me maybe 5 or 6 classes. So I have no time, because really next Wednesday, I want to say at least something about the general case of uniformization when the Riemann surface you want to uniformize is non-compact, because that's important also. So today I just want to give the main ideas, not all of them, but what are the main ideas to prove that this map is really a bijection. You get the full details in the chapter 7 of this book, which I think gives a complete proof of that. Okay, so again, I will only give some of the details. Let me begin by one of the important points, which for Felix Klein was really the most important point. For Felix Klein, it was not clear at all at first that this space is connected. And for him, it was like a discovery that if you think in a different way, it is obvious that the space is connected, and I want to explain that first. For him, it was really something important. So Klein observed that the space that I denoted by Riemann G is obviously connected because you can identify it with the space of Riemannian metrics on the surface modulo conformal equivalence homotopic to the identity. So why is it so? Well, this is this equality between these two spaces is just what I call the Gauss local uniformization. This is the Gauss local uniformization. If you give me a Riemannian metric on the surface, then locally you can make it conformal to an open set in C, and this local conformal map is unique up to holomorphic change. Therefore, the metric here gives you a complex structure. And conformally, and conversely, if you give me a holomorphic structure on sigma, you can construct a Riemannian metric whose underlying conformal structure is the given one. For this, you need two tools that Klein did not have at the time. The first one is you need the say infinity version of the Gauss uniformization theorem. I told you at the beginning that the proof of Gauss was only real analytic. For some reason, Klein didn't realize that the proof of Gauss was only analytic, and he just used it in the say infinity context. And this is true, as you know. This is true in say infinity. I mentioned that in the earliest lessons. So this is something that was not at the disposal of Klein, and something which is also missing in Klein's toolbox is the concept of partition of unity. If you have a surface with, say, a complex structure, you want to find a Riemannian metric on it in the right conformal class. You can do that in charts, and then you have to average them using partition of unity. In particular, it's not clear at all you can do that in the real analytic context. We know that today, but it's not clear at all. So anyway, this is also something that Klein did not see. But anyway, if you have that, and we do have that, because we know that Gauss' theorem is true in say infinity, we know that the existence of partition of unity. If you have that, then connectivity of this space is completely obvious. Not only connectivity, but even contractibility. Because if you have two Riemannian metrics on a manifold, you can just take the average. If you have Riemannian metric G1, or M1 and M0, well, you can construct T plus 1 minus T M1. And this is the path of Riemannian metrics on a manifold. Therefore, it is completely obvious that this space here is contractible. And therefore, when you go to the quotient is connected. So the connectivity of this space on the right-hand side is obvious from the Klein point of view. Note that this connectivity is very important because we are going to prove that these two things are in bijection by showing that this map is one-to-one. We did that already. Open and proper. So that would imply that the image of this map could be a connected component of the target. So to show that this is really a bijection, you need to have some connectivity on the target, and this is what Klein considered as his main discovery. It was important for him to realize that the space of Riemannian structures, the space of complex structures, is connected. Okay. So that's first observation concerning this. So let me make a few observations now concerning this space. A priori, it could be an awful space. You're taking the space of representations of a given group in PSL2R. Okay, this might be understandable. But inside that space, you take a subset, those representations which are discrete and injective. So first of all, it's not clear what kind of subset this is in the space of all representations. And the second problem is that you go to this quotient. And when you have a group acting on a space, sometimes the quotient is not so nice. So it's not clear at all that this space is a reasonable space. So you first have to make some work to understand better what is this space HOM, gamma, PSL2R, modulo PSL2R, discrete faithful. So let me explain a few of the main ideas me begin by something okay, so I told you I will not prove everything. I will just sketch a few of the main ideas. The first thing is this. Let us consider the space of all homomorphisms of gamma in PSL2R. For the time being, I'm not looking at this quotient, and I'm not looking at this part discrete faithful. What can be said about that? Well, one can say that this is an algebraic, let me even put SL2R. This is an algebraic manifold. Variety. That's very easy because this group is generated by 2G elements, A1, B1, A2, B2, AG, BG, with one relation, which is the product of the commutators is the identity. This is the presentation, the classical presentation of the group, of the fundamental group. Now, if you want to look at homomorphism from gamma to SL2R, you see from this presentation, we just have to take matrices which belong now to SL2R, such that the product of the commutators is the identity. And you see this is an algebraic relation between the coefficients. This is an equation for the set Hom S gamma SL2R. So this is really an algebraic equation. And indeed, this shows that this space is an algebraic variety. Now, it is not clear at all that this algebraic variety is smooth, and indeed it is not. So we have to work a little bit to understand where it is smooth, and you have to work a little bit to understand its dimension. Well, we could compute the dimension by just counting parameters. We have here 2G matrices. Each matrix is in SL2R. SL2R has dimension 3. So we have 6G unknowns. The coefficients of these 2G matrices. And here we have an equation, only one equation. This equation is a matrix equation. And this matrix equation, this matrix product of commutators has 3 dimensions. So we are writing 3 equations. So one could expect that the dimension of Hom gamma SL2R is indeed 6G minus 3. Because we are writing 3 equations and we have 3 6G unknowns. Now, we could also expect, if we take quotient by the conjugacy, if it makes sense, we could expect that the dimension of the quotient space by conjugacy is 6G minus 3 minus 3, because we are taking quotient here. And indeed, this is the case. away from the singular points. So I will be more precise with that. Well, we should be very careful with this kind of argument because sometimes it goes completely wrong. There's a good example in the notes of Thurston that I like very much. Thurston makes the following observation. Suppose that instead of having a surface dimension 2, you go to a 3-manifold. Let's say a compact 3-manifold. And suppose that your 3-manifold is hyperbolic, which means that its fundamental group is a discrete subgroup of the group of isometries of the Poincaré ball. And the group of isometries of the Poincaré ball is PSL2C now. And now let us try to play the same game that we played here. And let us try to compute the dimension of the homomorphism space. Dimension of hom pi 1 m, let's say SL2C. Well, what you need is a presentation for a fundamental group. Now, how can you get the presentation for the fundamental group of a 3-manifold, hyperbolic 3-manifold? Well, your hyperbolic 3-manifold, you can think of it as being some kind of polyhedron, and you identify faces 2 by 2, just like you do with surfaces. You have you have seen these polygons, and polygons you identified sides 2 by 2. Now, when you do that, you can even assume that all the vertices here, when you go to the 3-manifold, go to the same point. Just like we have here a polygon, all the vertices of the polygon, when you construct the surface, come to the same vertex. Now, you get in this way a presentation of fundamental group. You have one generator for each edge on the polygon, because each edge, when you go to the identification, each edge becomes a loop, and each two-dimensional face of the polygon gives you a relator, because you read on the boundary a loop which is homotopic to the identity. So if you do that, you have a group generated by a number of elements, this number being equal to the number of edges, and the relations being the number of two-dimensional faces. So now you can write the Euler-Poincaré condition for this polytope. You have that the number of vertices. Let me go to the quotient. If I go to the quotient, I get a cellular decomposition of the 3-manifold, having one cell of dimension 3, having k cells of dimension 2, L cells of dimension 1, and one cell of dimension 0. Now, if I write down the fact that the Euler characteristics of the 3-manifold is 0, I get that 1 minus k plus L minus 1 is equal to 0, so k is equal to L. Therefore, the fundamental group of the 3-manifold has the property that the number of generators is equal to the number of relations, which is very different from what we had in dimension 2. We had a huge number of generators and only one relation. here we have many relations and the same number of generators and relations. Now, if I want to compute this dimension using this intuitive count, I get that I want to count the dimension of pi 1m into SL2C. Well, for each generator, and I have L generators. For each generator, I have to choose a 3 by 3 matrix. So I have 3 L complex unknowns. I want to look at the quotients. I have one relation for each two-dimensional cell. So I have 3K relations, complex relations. And I should subtract -3 because of this quotient. So if I do the count, I get the dimension of pi 1m SL2C modulo SL2C over the complex numbers should be -3. Okay? Of course, the dimension cannot be negative, so there is something wrong somewhere. And what is wrong? There's not many places where it can be wrong. What is wrong is that these relations here, which are relations in the group, in the fundamental group here, turned out to be non-independent when you go to SL2C. So this means that in SL2C, there must be some relations which abstractly are independent, but seen in 2 by 2 matrices are dependent. And Thurston gives a good example that I think is very interesting to explain why this negative number can occur with no strange negative number can occur. He says this. And this is an exercise. I like this exercise. In hyperbolic geometry, suppose you have two, let's say A and B, two elements in PSL2C. Suppose they are hyperbolic and with distinct disjoint axes. So we are on the hyperbolic ball. A is a hyperbolic element, and B is some other hyperbolic element, and you assume that the axes do not intersect. Assume that some relation happens between A and B. Assume that. Then the exercise is then show that if you replace all A's by B's and all B's by A, you get a relation which still holds. That B M1 E N1 B M2 A N2 A and K is also equal to identity. So this is something that I like very much. It tells you that in PSL2C, some relations between two elements can imply some other relations. But abstractly, this is not true. If you take a group, the most general group, and if in a general group you have a relation like that, in general, this relation does not imply this relation. And I must say that this is a good example. This kind of phenomenon must occur in all cases of hyperbolic three-manifold, because otherwise you would have negative dimension. And it would be very interesting to understand what's happening here. I mean, so this is not correct. And the explanation for the fact that this is not correct has to come from this kind of phenomenon, which, to the best of my knowledge, has not been completely understood. So this is, as you know, in dimension 3, we have Mostow theorem, Mostow rigidity theorem, which tells you that this is not a -3, of course, but this is 0. In other words, if you can embed the fundamental group of a three-manifold discretely and co-compactly in PSL2C, then you can do that in a unique way. So there is no deformation of that. And this this is in the notes of Thurston. He says that this negative number is a hint that it should be rigid. It's not a proof, of course. It's just a hint that there is some rigidity. Nevertheless, in dimension 2, of course, Poincaré was not aware of that. But in dimension 2, it turns out that this is okay. But of course, this requires a proof because what I told you. Let me state a few results. So here's the first fact. You consider a group gamma, and you just assume that it's finitely generated, or even presented, if you wish. But if you don't like this generality, you think fundamental group of the surface of genus G. Now you consider, as we are doing, the space of homomorphisms from gamma to, say, SL2C. This is an algebraic variety. I could even put SLNC, algebraic variety. And the claim is that this algebraic variety is smooth on the irreducible part. So I should explain what I mean by that. A representation from gamma to SLNC is just a homomorphism from gamma to SLNC. And then one says that such a representation is irreducible if there is no subspace in Cn which is gamma invariant. No non-trivial. So definition, a homomorphism phi from gamma to SLNC is irreducible if any subspace V contained in Cn, which is gamma invariant, is trivial. So inside the space of all representations, you can look at those which are irreducible. It is a subspace of that space, and the claim is that this subspace consists of smooth points of this algebraic variety. This is not very difficult. Now, of course, comes the problem of working up to conjugacy. And then, here I'm not working up to conjugacy, because it's just homomorphism from gamma to SLNC. Now, how to work up to conjugacy? So you want, let's say, to look for homomorphisms gamma, let's say, to SL2C or SLNC. You have two representations, phi 1, phi 2. And you would like to say that they're equivalent if they are conjugate. And the question is to understand homomorphisms up to conjugacy. And then it is amazing that Poincaré understood completely this picture with no proof. But he makes the correct statements. I'm going to explain to you these statements. Poincaré claims the following and does not give any hint about it. And it's amazing because it has been proved 50 years later. The theorem is this. Of course, if two matrices are conjugate, they have the same trace. So you have trace of phi 1 of gamma is equal to trace of phi 2 of gamma. And the question is this condition sufficient to guarantee conjugacy? And here's the theorem. This is a theorem that Poincaré is using with no proof. If phi 1 and phi 2 are irreducible, representations of gamma. Gamma is any group, not necessarily a fundamental group, not necessarily countable, any group. If the traces are equal, for all elements in the group, then the representations are conjugate. Now, if you look in traditional books on representation theory, you find this theorem traditionally for finite groups. For finite groups, I think it's classical fact. It says that two representations, irreducible representations of the same finite group, are conjugate if and only if they have the same so-called character. The character being defined as the trace of the matrix elements. But the fact is that this theory, of course, the groups you are dealing with, the fundamental group of surfaces, etc., are not finite. So obviously, Poincaré knew this fact for finite groups, we just generalized it to any group. This is standard. Let me, I will not prove it, but let me give you a sketch of the proof of this, which, to the best of my knowledge, I found that statement for the first time in André Weil, 1960. Before that, I did not find, I found it in Poincaré, but I didn't find it proved anywhere. So here's a sketch of the proof. The sketch of the proof is this. First, there's a lemma. First lemma is this. Actually, I could put even better G, L, and C. Okay. The lemma is this, which is due to Burnside. Again, Burnside proved it for finite groups, that his proof is correct for any group. It says that if a group has some linear representation which is irreducible, then the algebra generated by matrices, generated by phi of gamma in matrices, n by n matrices, is the full algebra of all matrices, is equal to M and C. So it says that any n by n matrix can be obtained as a linear combination of the matrices which are in the image of the group. That's not so hard, but that's interesting already. Each time a group is acting irreducibly, it is so big that the set of matrices that you get generates the full algebra of all matrices. The second lemma, which is also elementary, I don't know who proved it, but it's really like, let me put it as an exercise. It says that any automorphism of M and C as an algebra is inner. So A, let's say, X, M and C goes to A, X, A inverse. So if you look at this space of n by n matrices as an algebra of matrices, if you look for automorphisms of this algebraic structure, the only way to construct an automorphism is to conjugate by some matrix. That's not difficult. Now, if you have that, let me show you how to prove this theorem. The trick is this. Suppose you have two representations, phi 1, phi 2, with the same traces. So you assume trace of phi 1 gamma is equal to trace phi 2 gamma for any gamma. And now suppose that some linear combination of some matrices for the first representation is 0. So phi 1 of gamma I suppose you take a certain number of elements in your group, gamma 1, gamma 2, gamma k, take their images by the first representation, and take some linear combination. And suppose it's 0. I claim that this implies that the same relation holds for the second linear representation. Assume that for a moment. If this is true, okay, so assume that. If this is true, I can easily construct an automorphism of the algebra MNC. How do I do? Take a matrix A in MNC, in A belonging to an n by n matrix. By the lemma of Burnside, any matrix is a linear combination of elements in the first representation. So the matrix A can be written in some way as a sum of alpha I phi 1 of gamma I. Of course, this is not unique. A given element A probably may be written in many ways in this linear combination. However, if I decide to send, let me call it X, sorry, X. If I decide to define, let's say, theta of X as being the same sum, where I use here the second linear representation, this will transform a matrix X in some other matrix theta of X, and this operation is well defined, because this expression of X as a linear combination of phi 1 gamma I is not unique, of course, but it is unique up to some other combination which is equal to 0. And this lemma here, this thing I didn't prove yet, shows that if this is equal to 0 for phi 1, it's also equal to 0 for phi 2. So if I take any matrix, if I write it anyway in this, as a sum of combinations in this way, if I substitute 1 by 2, I get another matrix, and this transformation from X to theta X is well defined. And this transformation theta X is, of course, an algebra automorphism. Theta is an algebra automorphism. And since it's an algebra automorphism, it has to be an inner conjugacy. So that means that theta is nothing more than a conjugacy Okay, so now let me write this equation in the special case where X is equal to phi 1 gamma. Of course, the image by theta of phi 1 gamma is just phi 2 gamma. So it follows that phi 2 gamma is the conjugate of phi 1 gamma by A. And indeed, I proved that the two linear representations are conjugate. Okay, so it's very simple. As soon as you believe this lemma of Burnside and this exercise. By the way, I just checked this morning. You find this in elementary textbooks in algebra. Take the Serge Lang algebra. This is explained in full detail. So I have to prove that. Well, Okay, so suppose this sum is 0. So what I can do is that I can multiply this 0 by anything, it's still 0, and take the trace. So let's multiply that by another combination. Of course it's 0 because this is 0. Now let me take the trace of 0. Trace of 0 is 0. So this is sum trace of phi 1 gamma I phi 2. Sorry. Trace. Sorry. Phi 2 delta j is equal to 0. So this is the sum of alpha I beta j, trace of phi 1 of gamma I delta j is equal to 0. Now I can use the assumption. The assumption is that traces are the same for phi 1 and phi 2. So this quantity here is equal to the same where I replace 1 by 2. So this is equal to that. So this is equal to that. So this quantity is 0 for all choices of beta j. But I told you that this generates M and C. So this matrix here, what should I say? Sorry. Trace. Okay. So this matrix here has the property that if I multiply it by any other matrix, the result has trace 0. But the function trace is a non-degenerate bilinear form. If you have a matrix whose trace is equal to 0 and whose trace multiplied by any matrix is 0, the matrix is 0. Okay, so I can put it this way. The function, let's say, x1, x2 in MNC gives trace x1, x2 belonging to C. This is a bilinear form which is non-degenerate. So if you have a matrix x1 which is orthogonal to all matrices, it is 0. So if you have this matrix here, you know it's orthogonal to all matrices, it is 0. So therefore, the sum alpha I phi 2 gamma I is also 0, and this is the lemma. Okay? Well, this is pure algebra, but this is beautiful. Sometimes algebra is beautiful. Eh? Okay, so anyway, this is something that Poincaré said explicitly, and I like the way he says. I mean, his comments about that prove that maybe he had a complete proof of it, I don't know. Maybe it was too easy for him, not clear. The next thing that Poincaré says is a finiteness theorem. Here's the statement. It goes beyond that. The theorem is this. Start with gamma, let's say a finitely generated group. And you want to look at homomorphisms, representations from gamma in G, L, and C. Then the statement of Poincaré is this. Then there is a finite number of elements in the group. Finite number. Such that if phi 1 and phi 2 are irreducible and have the same traces, not over all elements in gamma, but over this finite set of elements, then they have the same trace for all elements. For every element. So if you want to check equality of traces of two representations, which a priori requires an infinite number of checks, you have to check this, that these two numbers are equal for all gamma, and gamma is infinite. It is enough to check equality on a finite number of elements in the group. And this finite number is completely explicit, and this yields to what's called the traces identities. Trace identities. See? Let me just give you one. Well, this is not hard, but this is interesting. Let me give you one example of a simple statement which I think is interesting. Suppose you take a word in two letters. So W is a word in A and B. So for example, W is A, B, A inverse, B7, A2, B minus 3. And suppose you want to compute the trace of this word when you evaluate it on two matrices, A and B, where A and B are matrices in SL2C. Then the theorem or exercise or whatever says that for every word there exists a polynomial PW in three variables with integer coefficients such that this trace of the word evaluated on these two by two matrices is just taking this polynomial and evaluate it on trace of A, trace of B, trace of AB. So that means that if you know the trace of two matrices, and if you know the trace of their product, then you know the traces of all words in A and B. And this polynomial, you can easily compute it from the word. I mean, I did that on my Macintosh. You take a word, and it will produce a polynomial. You put trace A, trace B, trace AB, you have all traces of all words. So you see, that means that you can evaluate traces. That's a special case of this theorem of Poincaré, when n is equal to 2, and when the group is generated by 2 elements. It tells you that you can compute traces of very complicated words just from the data of 3 computations: trace of A, trace of B, trace of AB. Okay, that's one find that that's explicitly in this classical book by Klein, Fricke Klein. Fricke Klein. This book by Fricke Klein was published, I forgot exactly when, but it was an attempt for Klein later to claim that he did everything without Poincaré. But that was not convincing. Fricke and Klein was published in 1912, so the year of the death of Poincaré. So, but anyway, this book is wonderful. If you can read German, or if you can just guess German, which is my case, that's a wonderful book. Okay, all of this is very good for Poincaré because it enables you to understand representations up to conjugacy just by a finite number of traces. It tells you that if you want to understand the space of linear representations of the fundamental group of a surface, it is enough to understand a finite number of traces of the images of a finite number of specific elements in the group. Now, next step that is very important in the proof of Poincaré and Klein is the following. And this is explicitly explained in Poincaré and Klein. It says the following. This is the following theorem. In Hom gamma PSL to R, so all representations from the fundamental group of a surface of sigma of genus G to PSL to R, the subspace of discrete and faithful representations is open. So you start with a representation of the fundamental group of a surface on the Poincaré disk, which is acting freely, properly, discontinuously. You change a little bit the representation, and by some kind of miracle, after this perturbation, the new representation is still discrete, free, proper, etc., and continues and still defines a Riemann surface. So let me explain how one can see it quickly. So proof. This is basically the way Poincaré does. Well, suppose you have a, let's say, genus 2. So you have A, B, C, D is equal to identity. Suppose you have a representation of this group on Poincaré disk, which is discrete and faithful. Well, that means that this group defines a Fuchsian group. So you pick a point, and you look at its image by A, by B, by A inverse, by B inverse, by C, by D inverse, and you come back at the original point, because you have this relation. So what you have is that if you pick a point, you create a polygon with 8 sides. 1, 2, 3, 4, 5, 6, 7, 8. You start with a point, and you create a polygon. Well, you have seen that this polygon is a fundamental domain. This polygon, by definition, is such that the A, B, A inverse, B inverse, C, D, C inverse, D inverse. It is clear that these sides have the same length, and it is clear that the sum of the angles, interior angles, is 2 pi, because this is the identity. So now you just perturb this representation. You want to show that this representation is the space of open, the space of faithful, discrete representation is open. So you just perturb a little bit the matrices. So you take A prime, B prime, C prime, and D prime, which are close to A, B, C, D. And of course, since it's still a representation, you continue having the product A prime, B prime, C prime, D prime is still the identity. Well, now it's clear. You take your point X, and you will create another polygon which is close to the first one, because A prime is close to A, B prime is close to B, etc., etc. And this new polygon, you still do not know that this is fundamental domain for a group, but this new polygon satisfies the assumption of Poincaré polygon theorem. It is a polygon, convex polygon, and this polygon has the property that this length is equal to this length is equal to this length. The lengths are equal 2 by 2, and the sum of the angles again is 2 pi, because this identity is satisfied. So that means that we can apply the Poincaré theorem. This new polygon is indeed the fundamental domain for some Fuchsian group. And this Fuchsian group, let me call it, this Fuchsian group is discrete, faithful representation of the same group gamma. So it's kind of a tautology. I mean, this property that this is open is just a restatement of the theorem of Poincaré, that if you have a polygon with the correct sides and the correct angles, then it does tessellate the plane. So you really have this open property. More interesting is that you have the closed property. I mean, the space is not only open, but it's closed. So let me explain that. And therefore, since it's open and closed, that means that the space of a discrete, faithful representation is one connected component of this full representation space, since it's open and closed. So to show it's closed, so this, I think Poincaré did not notice it. The proof is this. a sketch of the proof also. So you suppose it's not true. So you would have a family of representations, phi sub n, in SL2R, such that all of them are discrete and faithful. And such that phi n of gamma converges to some phi infinity of gamma, where phi infinity is not injective, or not discrete. And then the trick is to use what we call today Zassenhaus principle. Zassenhaus principle. Well, it says the following. Suppose you have two matrices, A and B in SL2R. And suppose they are close to the identity. So the norm of A minus identity is small, and the norm of B minus the identity is small. Then look at the commutator, AB. And the principle is that if you look at the distance from the commutator to the identity, it is even smaller than the two of them. So it's less than epsilon squared. Let's say epsilon small enough. That's very easy to see. If you take the map A, B in SL2R cross SL2R, goes to commutator AB, A inverse, B inverse in SL2R. And if you look at this map as a smooth map from this three-dimensional Lie group cross itself to itself, and if you look at the derivative at the origin, take derivative at identity, well, you see that you compute the commutator of identity plus something, a small matrix, and identity plus some other small matrix. And you see matrices close to the identity up to second order commute. So this commutator is identity plus second order. But I don't go into the details. That's something that can be done easily by hand. So that shows that if you take two matrices which are close to the identity, the commutator is even closer to the identity. And then when you have that, you try to understand what's happening if a sequence of representations converges to a non-discrete one. And then you say, well, if the image is non-discrete, that means that in a small neighborhood of the identity, I will get many elements, and taking commutators, I'm looking at the clock. Well, I'm sorry. I want to stop this proof here because I'm looking at the clock, and really I want to explain the key argument in Poincaré and Klein lemma, and this is not the most important one. So I should not have gone into this. Open is okay. Sorry, closed is not okay. I did not give the proof. I can just only tell you that this is not complicated and is based on this principle. Sorry, I don't go further because I want to go to the last key point. The last key point is something that neither Poincaré nor Klein could have guessed. Is this. The last point is this. I want to show that the map from faithful, discrete, and I told you this is a connected component of some algebraic variety, so it's a smooth manifold, goes to what I call Riemann G, which is the space of Riemannian metrics on the surface modulo conformal homotopic to identity. Okay, so we know this is more or less, we know this is a manifold. This is connected. We have seen this is injective. And then I want to say it's proper. Is a proper map. This is what's missing to show that this is bijective. You have an injective map from a manifold to another manifold of the same dimension. If this map is injective and proper, if the target is connected, this map is bijection. So how to say it's proper? Well, you have to take a sequence of elements here. So it's sequence of representations, phi k, sequence of representations from pi 1 of the surface to PSL to R. And you have to assume that corresponding to this sequence of representations, the sequence of Riemannian metrics that you get converges. So you assume that, let's say, the Poincaré disk divided by phi k of pi 1 sigma converges to some limit, to some Riemannian metric. On sigma. And then you have to prove that the family phi k as a family of linear representations is bounded. Or if you prefer, using what we have seen today, you have to prove that the traces of phi k of gamma are bounded as a function of k for each gamma. So you are given this sequence of representations, which are faithful and discrete. Each one of them gives you a metric on the surface with curvature -1. And you have to show that if this sequence of metrics converges as metrics, this gives you a bound on the representations. And representations are measured by the traces. And the trick is to use the so-called extremal length principle. Length principle. So let me explain that quickly. You have a surface. On that surface, you have a Riemannian metric. Let me call it M. And on that surface, you have a homotopy class. Let me call it alpha, a homotopy class. Then what you do is this. What you can do is you can measure the length for the metric M of any curve C in this homotopy class. You can minimize this over all classes, over all curves in this homotopy class. This gives you the length of the closed geodesic in this Riemannian metric. Now you want to do something that would be invariant under conformal transformation. So what you do is you take this and you replace the metric M, you replace it by some other metric, or you multiply by some function rho. Okay? Now this is a function that depends on the function rho. So to make it homogeneous, you take its square and you divide by the area of the surface sigma as measured with the metric rho m. This still depends on the choice of a metric of a function rho, and you maximize that over all functions rho, which are smooth functions from the surface to R plus. This is called the extremal length of the homotopy class alpha in the conformal class of M. So this is called the extremal length of alpha in the conformal class M. Of course, you have to prove that this is a finite number. You do that. You find that in Alfor's conformal invariance. And then the trick is this. If the sequence of metrics converges, this tells you that this sequence of extremal length, if this sequence of metrics is bounded, this tells you that this sequence of extremal length is bounded. But of course, among all these metrics here, for each k you can choose the hyperbolic metric. And this gives you a bound for the length of the homotopy class in the hyperbolic metric. And the length of the homotopy class in the hyperbolic metric is given by the trace in SL2R. So you get an upper bound. You get that the trace of phi k of an element gamma is bounded by those extremal length. And this gives a bound for the traces and hence proves that the family of representations stays in the bounded domain, and then you have a limit. And this indeed is the, sorry, it was quick. It's a sketch of the proof of the properness of the map from Fuchsian groups to Riemann surfaces. So that was not clear. I'm sorry about that. Let me say a few words. You take a sequence of Fuchsian groups converging here. So that means that the sequence of Fuchsian group converges as metrics, Riemannian metrics. You use this extremal length principle to get a number which gives you a bound on the traces. And since traces are define the linear representation, this gives you a bound on the linear representation. You have and you have properness. So that's the final point of the proof of Poincaré and Klein. Okay, so I will stop here. So again, you have noticed that I did not give at all any kind of full proof. The full proof, again, is chapter 7 in the book. It's rather long, but all the arguments are elementary. You see what I did today. I mean, you have to put all these things together. But I wanted to not to finish, but I want to finish the description of compact Riemann surfaces and uniformization today, because last lesson next Wednesday, I wish to say a few words about the uniformization for non-compact surfaces, which has been achieved by Kirby and Poincaré in 1907. And for this, I need to introduce you to the new invention of Poincaré, which is the balayage method. How would you say in English, balayage? Balayage, no? Balayage? Wait. Fascina. Okay, I don't know. Okay, so thank you. Thank you.